All right, cheers. Thank you. Thank you for having me here. Like Thomas said, I work at Foster & Partners, which is, well, for some of you, I don't need to explain that's what the company is, but we're a big architecture and design firm based in London. And to get a really quick overview, I just put this slide up, and that gives you an idea what we do, what kind of buildings we design. Anything from skyscrapers to airports to huge infrastructure projects, all the way to the new headquarters for Apple. And even smaller things like door handles. So different scales. And we do this, of course, all over the world. Right? We've been working, the practice has been in existence for almost 50 years, so we've built in a lot of places. Now, a few years ago, that map had to be updated quite a bit because we had two projects that didn't fit on that previous map. One was on the moon and another project was on Mars. The first one we did was for the European Space Agency. It was a collaboration with them where we looked at 3D printing habitat, a lunar habitat. And the second project was a competition that we did almost a year ago. That was for NASA, looking at, again, a 3D printed habitat for Mars. Now, how do you start a project like that? How do we start designing this? Well, we thought we're not really going to change the way we design. We're going to have the same methodology. So what we do, we're going to look at some precedents. Are there any precedents? Well, for the moon, that's kind of a bit tricky because the only precedent we have is the Apollo missions. And that was actually even before I was born. So it's a while back. And the other thing is that the longest time people were on the moon was about 3 days. And 3 days is like a camping trip. That's not living on the moon. So you need to take lots of other things in consideration if you're going to go and live on the moon. So a better reference, I think, is this one, is the ISS, the International Space Station. And if you look at that, as an architect, I look at the topology of it. And what do I see? Well, I see an assembly of modules, of cylindrical modules. A bit like this one, which is the Columbus module, which is the science lab for the European Space Agency. And it's a cylinder. It's like a can, a soda can. And why is it that shape? Well, it's very simple at the end of the day. It's the space you have in a fuselage of an Ariane rocket. That's about the space you can fit something in there. Now, so that limits you to what you can bring up into space, of course. The other thing that limits you is gravity. Now, gravity is very expensive. It costs a lot of money to kind of really escape gravity. Bringing a kilogram to the moon will cost you, depends what kind of calculation you use, but something like 200,000 euros a kilogram, right? So you want to have something that is more compactable and is lighter. We work a lot with inflatables. So this is a project we did in Canary Wharf. It's a new Crossrail station, and we use the roof is covered by inflatables, ETFE panels. And why is that? Because the roof structure is made of wood, and glass would have been too heavy. So we use an inflatable, it's lighter. It's compactable as well. So maybe that's a clue to use that in space. And that's not science fiction. Only a few weeks ago, the first inflatable module went up on the International Space Station. And so this is the first module that's completely inflatable, and the astronauts will now be able to open it and go into it and see how that works. So it's not such a crazy idea. So that's the basis. That was the basis for our moon base. So we started off with that standard cylindrical hard shell element that you can see there, where all the life support is, where the airlock is as well. And out of that we have an inflatable. It's a much larger space to live in, and it will be much easier to bring up because it's much lighter. Wherever we go in the world, wherever we design, we always look at the local environment, their environmental factors. We weren't going to change that. We're still looking at what are those environmental factors on the moon now. Well, first of all, there's no air, it's a vacuum, right? as 1/6 of the gravity as well. But those things are not the things that are really driving the design here. What really was driving the design was the fact that we had to protect ourselves from gamma radiation from the sun. Right? On Earth we have magnetosphere, we have an atmosphere that protects ourselves from that. On the moon you don't. So protect ourselves from that. We need to protect ourselves from micrometeorites. Those get burned up in our atmosphere. On the moon you don't have that. That's why the moon surface looks like this. And those things are, well, they're quite fast. If you look at a bullet, that goes about 1 kilometer a second. If you look at a meteorite, that goes at about 18 kilometers a second. So, you know, it can do some damage. And also huge temperature differentiations. So we have up to plus 100 to minus 160. And that could happen on the same structure. So we need to protect ourselves. And we're doing that with a shell structure on top of our inflatable. And that shell structure needs to have mass. You know, we did lots of calculations with our collaborators as well on this to see what the actual thickness would be of this. I'm not going to get into that now. But what we needed is mass. And I've just told you as well, mass is very expensive. So we're going to do something extremely sustainable. We're going to use local materials, right? So what we do in the world, if we go to a certain country, we build in different areas in the world, we'll look at what is there, what's available. Is more concrete, more wood, more steel. What do we have here? Well, not that much. We have a lot of dust, which we call regolith. It's moon dust, and we have loads of it. So what we will be doing is we would use that dust as the base material for the 3D printing. And instead of making a big 3D printer, then kind of print something that's smaller inside, if you see all the printers in the fair here, no, we're going to go the other way around. We're going to have a small printer, which is a bit more like a rover, that will scoop up dust from around the structure, bring it to the dome, and then solidify it layer by layer. And you can see here a little bit how that could work. You have the shell structure, you have an inflatable, pump it up, and then around it you start bit by bit, layer by layer. We have our 2 little robots printing a structure on top of that. There you go. Now, I mentioned there was not only a moon base, there was also a Mars base. So this is our Mars base, which is quite similar in concept. And you know, we had to protect again for the same things, temperatures, gamma radiation and so forth. So we needed that dome structure around it again. But there was a bigger problem we had here, which was Mars is really far away, right? And to put it in context, if you look at the International Space Station, it's actually quite close. It's only 400 kilometers above us, this thing floats. If you then go to the moon, the moon is, and this is in scale actually, the moon is about almost 400,000 kilometers away. So 1,000 times the distance from the International Space Station. If we then go to Mars, and this is a picture of Earth taken from Mars by the Curiosity rover, the little dot that you probably don't see it, right? It's a tiny, tiny dot. 400 million kilometers. So another factor of 1,000. What does that mean? Well, that means that there's no direct radio contact possible at all between Earth and Mars. There's, depending where you are, where Mars and Earth are, let's say there's about 20 minutes delay. So if we're thinking that we can control these rovers from Earth to do things, well, you might give it an instruction, go left, and it might go left 20 minutes later, and then 20 minutes later again, it will tell you if it went left or not. And, you know, so that's actually quite an issue. So instead of looking at Curiosity as a good example, where you have one very expensive machine that does everything, and it's kind of half teleoperated by Earth, very, very slowly, we thought, well, this is a better example to look at. Ants, swarm behavior. Let's build cheaper, smaller robots, not 2 robots like we had on the moon. We have more robots, maybe 100, and if some of them don't make it, if some of them break, it doesn't matter. it could still work. Excuse me. So these are the robots that we envisioned. So we have the bigger one, which is our digger, and that would dig out the regolith from the Martian surface. We have the second one, which is a transporter that could take the regolith and move it towards the base. And the third one is our melter, and that would take the regolith and melt it together through microwave technology. So that's the kind of problem. You can see it happening here. In the background, you see the big digger digging up the regolith, and then a few transporters bringing up the dust. And then in the front, we have these melters that don't need to move that far. They just kind of melt layer by layer of this regolith together. And this idea of redundancy, we didn't only build into the fabrication process, but in the whole habitat. So instead of on the moon where we had the base module would be one cylinder with an inflatable, we actually divided up. There's 3 elements coming together, right? And each of these elements, they're also kind of inflatable elements, as you can see here. They kind of open up like an origami piece. Each of these elements are self-sufficient, so we can actually swap them around. If one completely breaks down, the lab could be moved to the living space and so forth. So it's actually all quite modular in design. And as you see here as a raised floor, the floor area is where all the life support sits. So if only one module arrives, that could actually work on its own as well. But what was different here on the Mars project as well, that we still had a bit more time to think about what it would be to live in that base. So we tried to see what would the interior be like. And if you look at, again, to the International Space Station, that's what it is. So this is when you have engineers designing a space station completely, right? There's not really any designers involved. Lots of laptops with Velcro on the ceiling. And then the other one, if you then look at movies, science fiction, this is the movie Moon. It's amazing how many corridors there are in science fiction movies. You ever thought of that? You know how expensive space is in space? But like all science fiction movies have loads and loads of corridors, right? And this is very clean, very clinical. Is this a space you want to live in for like 3 years? I don't know. So we wanted to look at an example, an analog of something that has happened before. And we came up to this thing, which is Halley 6, which is the Antarctic base, the British Antarctic base. And I started to know John Eager, who was the winterization commander of the base. And I had long chats with him. And it was really interesting, because that place, Halley 6, is cut off, I think, almost for 8 months a year, completely from the rest of the world. There's no evacuation possible. You can't even be evacuated from the ISS, not from this place. You're stuck there, right? Communication is also quite difficult. So we thought, well, this is a good place to look at on how people live there, right? Space is also quite small. So this was why, when it was first commissioned, this is one of the pictures there. And John told me that, well, we're actually living and we're working in the same space. And the spaces are more designed as a working environment than a living environment. So what he was missing, and this is a word he always said, was like something tactile materials they're missing. And a nice example of what they did this. So they took some of their shipping crates and they built a nice wooden wall. Right? And so they started to actually change their environment to what they actually needed. So I thought it was quite interesting. So we thought, well, why is there not a wooden floor? Why is there not, in our space station, why do we have a thin veneered wooden floor? People have to live there. This can't be just a lab environment. So we started to think a bit like, how would we design it as a living environment? The other thing was, big question I had, do people live in their own little rooms a lot? How much time do they spend in their own rooms? And apparently this is the private rooms shared with 2 people in Halley 6. And apparently people spend very little time there. So we made the decision to make the berthing spaces on our Mars base actually quite small. They're small spaces, you can't even stand up in them. Right? Now, we're not the only designers that looked at space. Even back in I think it's the 70s, isn't it? Skylab is the first space station by NASA, there were designers involved. There was Raymond Loewy involved. He was one of the main designers. He had a contract with NASA to look at the interiors of Skylab. And his biggest contribution, I think, is the thing just next to him, is that window, right? Because from an engineering perspective, there's no need to put a window in Skylab space station. Why did it need to? Why did it need to look outside? There's cameras, all sorts of things. So there was actually no need for it. There was a huge fight between the designers and the engineers to actually do get that window. In the end, they did get a porthole in. And even on the ISS, International Space Station, this was the biggest windows they had up to, 2001. Only a few years ago, they put in this one, the cupola. And this is becoming now almost an icon for the International Space Station. It's kind of the most famous place in the space station. And, you know, all the best pictures, and the astronauts love to hang out there, look back at the Earth. Here it is, you know. See how happy he is? But also notice how many flaps there are to close it off. And from an engineering perspective, from a risk perspective, this is a really big problem, that big window. It's quite a risky thing to make. It's very expensive. So you probably think I put massive windows now in my Mars base, right? No, I didn't. We didn't put a single one in. Because of that, we thought here's a huge risk to put it in. And we had this massive shell structure around it. How would we do that? But we thought people do need to look outside. So we started to work with screens, right? So big, really high resolution screens that could probably project Mars outside, what you just would see on the outside, but maybe project things like a forest back home, or project a movie or whatever it is. So you can actually play with it. So it would act as a window as well, not just as a screen. And we even looked at a skylight, not a real skylight. We're looking at some technology that is now being used a lot in London, where they are digging out lots of basements in Chelsea and South Kensington, where they want to have feel that they're actually in a basement, and they need skylights. These are artificial skylights they're putting in. So we thought, well, that's the kind of interesting technology to have there, because we can't have a skylight, but we can have an artificial one. So you might think, well, this is all great, but at the end of the day, this is just paper architecture, right? You just like make these things up. But we want to actually push it a little bit further as well. So for both the Moon and the Mars project, we took it that little bit further. And we thought, let's go and print and build a few things here. Yeah? So this was a shell, like a section out of the shell structure of the Moon base. And we worked with, I think he was here yesterday with Enrico Dini, with his company, with D-Shape, to start building a part, to actually have a look at it. What would that look like? And so this is the first, there's quite a large 1.5 ton 3D print that is now exhibited at the headquarters of the European Space Agency. And you notice that it's actually much thicker than the design. You can see that here. Well, the reason for that is that, of course, we designed it for the Moon, 1/6 of the gravity, but we had to build it on Earth, so it had to be thicker. But that was just like a mock-up. We also wanted to understand, does the 3D printing process really work in a vacuum? Because on the Moon, we're going to have a vacuum. So we worked with Alta, which is a space engineering firm in Italy. Excuse me. And they have huge vacuum chambers. So in their vacuum chambers, we had a small setup to see if we could 3D print a very small part, see if that would work in a vacuum. And you won't believe it, I was extremely excited about this little sphere. That was the first 3D print ever done in a vacuum. And even further with the Mars project, we also wanted to push it that slightly bit further, not just have the beautiful rendering. So we thought, well, you know, it's all good and well us talking about these swarming robots. Let's see if we can make that happen. So we thought, let's make our own robot. So a few months ago, we were at the Smart Geometry conference with our team, and we tried it out. We tried out, built a few robots, a few little rovers. They were all the same, so they were a slight modification. They could dig and deposit sand. You see the guys working on it. So we had 6 tons of sand, a big sand box. And all of these robots, they're not teleoperators, so they're actually given a task. They're giving a task, get some sand from here to there. Each of them had their own processor, and so there was not an overall control system that controlled each of these robots. No. If they then would actually bump into each other, they had to make a decision what their next task would be, how they adjust their task. I see them here working. I think the next thing is a video, if you can play that. They were moving quite slow, so we had to speed this up a bit. And I think to finish it off, I'll just show a quick video of our moon project. Can you put the volume up?
Planet Earth is protected by the atmosphere, the layer of air and gas that surrounds it. The atmosphere shields the Earth from solar radiation. It keeps the temperatures balanced, and it protects us from meteoroids. The site of our lunar base is the Moon's south pole. Conditions on the Moon are very different from those on Earth. Because the Moon has no atmosphere, there is no protection from solar radiation. The temperature fluctuates, and there is no protection from meteoroids. The lunar lander has detached from the rocket launch and is on a course to Shackleton's crater, the Moon's south pole. Attached to the lander is a cylinder which contains an inflatable dome and 2 robot 3D printers. After the cylinder containing the habitation capsule has been unloaded, a dome is inflated from one end. This provides the support structure for construction, a little like scaffolding is used to build on Earth. The lunar habitation is built by a series of robot-operated 3D printers. At one end, it has a scoop to collect the regolith. In the center are the containers for the printing material. At the other end, there is a robotic arm with a printing head. The robot collects regolith from the Moon's surface. Layers of this moon dust are built up over the dome to create the protective shell. This process takes about 3 Earth months. The shell is made up of a hollow, closed cellular structure. Under a microscope, it would look very similar to the structure inside a bird's bone. Like a bone, it is light and incredibly strong at the same time. When the lunar base is complete, it can house 4 people. Inside the dome, they're protected from solar radiation, meteorites, gamma radiation, and high temperature fluctuations. The original capsule functions as an airlock and technical support module. The skylights draw daylight into the living and workspaces, which are sheltered within a pressurized enclosure. This method is a pioneering advance in space-age construction. At Foster & Partners, we're used to designing for some of the world's most extreme climates. We often use materials found locally to create sustainable buildings on Earth. While the Moon is an exciting new territory for architecture, the value of this logic endures.
All right, that was it. Thank you very much.